Hello and welcome back. In today's video, I'm going through exercise 1.29 from the Art of Electronics. This exercise is split into two parts. So for part A, we need to show that adding a series capacitor of value C equals 1 over omega squared L makes the power factor in the circuit equal to 1. So the circuit being a series RL circuit. To get a better understanding of what the question is asking, let's first discuss what power factor means. Power factor is basically telling you the efficiency of a inductive or reactive system, and it's simply kind of the measure of evaluating how effectively you're using the incoming electrical power in your electrical system. So if the power factor is closer to 1, it means that you have a more efficient system. And if the power factor is dropping below that, so lower than, let's say, 0.8, then you have a bad power factor. So the power factor is basically a proportion, so obviously it doesn't have a unit, and is calculated by dividing the true power, which is on the red axis. So that's basically power going purely to the resistive load, divided by the apparent power, which is this line over here. The apparent power is equal to the square root of the reactive power, which is Q, and the true power squared. So that's this equation over here. You can see on the screen I've put down some units. So reactive power is measured in VAR, which is volt ampere reactive. Apparent power is volt ampere, and obviously true power is watts. Another way you can look up power factor is basically the power you dissipate in your resistive load divided by the power you dissipate in your impedance. So for this question, we are looking at the power factor in a RLC circuit. For the part A of the question, we have a circuit that's series. So we have this resistor here and the inductor, which is given to us from the question. And then we are asked to introduce a capacitor whose value is 1 over omega squared L. So L being the value of the inductor. Then we are asked to show that the power factor is equal to 1 with the new capacitor added in. So let's look at this circuit in more detail. The impedance of the inductor is equal to J omega L. And the impedance of the capacitor is equal to minus J over omega C. Obviously, our C is equal to 1 over omega squared L. So what I've done over here is replace the C with the value that's been given to us for the capacitance. Now, if I multiply this out, obviously we can cancel out the squared with the top there. So we end up with 1 over omega L. And simplifying this equation further, we basically end up with what we have here. So minus J omega L is the impedance of the capacitor in the circuit to the left. Now the total impedance of this circuit is equal to the impedance of the capacitor plus the impedance or the resistance of the resistor plus the impedance of the inductor. So if you plug in the numbers from above, so our XL is J omega L, our XC is minus J omega L. So we've replaced XC with minus J omega L. We've got the resistance here, and we have the inductance as plus J omega L. The minus J omega L cancels with the plus J omega L, and we end up with the total impedance of the circuit is as equal to the resistance in the circuit. So what this is telling us is that the total impedance is only due to the resistive component, and the reactive component in this circuit, by introducing the capacitor, is equal to 0. And if the reactive component is 0, then our power factor is equal to 1. This graph over here Obviously, we have the reactive power on the y-axis, and we have the true power on the x-axis. So our reactive power is equal to 0. So this line is collapsing to be the same as the red line. Therefore, our power factor is basically 1. For part B of the question, we need to show that adding a parallel capacitor of the same value as described before, so 1 over omega squared L, makes the power factor equal to 1 in a parallel RL circuit. What I've got here is a parallel RL circuit, so with R1 and L1, and then I've added a capacitor of value 1 over omega squared L, as described in the question. And obviously that is placed in parallel with the two components. So same as before, the impedance of the inductor is j omega L. The impedance of the capacitor is equal to minus j omega L. And the total impedance in this case is equal to 1 over the total impedance equals 1 over the capacitive impedance, 1 over the resistance, plus 1 over the inductive impedance. And you can relate this question back to when if you were just looking at 3 resistors in parallel. So now plugging in the numbers that we have from above, so j omega L is replacing XL, minus j omega L is replacing the XC, and then we have our R. Now simplifying this equation, we can get rid of this term and this term as they cancel each other out. We basically end up with 1 over xt is equal to 1 over R, and that basically means that xt, the total impedance of the circuit, is equal to R. Similar to part A, this is telling us that the total impedance of the circuit is only due to the resistive component. The resistive power dissipation is equal to the reactive power dissipation in this circuit after introducing the capacitor. So reactive power is 0, therefore the power factor is equal to 1. And obviously the same explanation stands that I showed you in part A. This is the solution to the question that's being asked of us here. But let's kind of talk a little bit more about what's actually going on. So why are we doing this? So why are we introducing a capacitor for a RL circuit? Now, if you imagine a RL circuit as being an inductive motor in an industrial power plant or something like that. So we can represent this inductive motor with the following components. Obviously, this is a very simplified model. So we have some resistance in series with some inductance. What I'm going to do now is basically give these components some values. We'll calculate the apparent power and the reactive power as well as the true power, and then go on to calculate the power factor for the circuit. We'll do this with just this component, and then we'll introduce the capacitance and we'll see what happens to the power factor and the calculations. Let's start off by defining our input voltage. So I'm going to set the input voltage as 240 volts with a frequency of 50 Hertz. And I'm going to set the size of the inductor to be 100 millihenries or 0.1 henries, and the size of the resistor as 50 ohms. These are just values I've picked randomly. Now let's look at the reactance of an inductor, which is equal to 2 pi. So 2 times pi times F times the inductance. So we get a inductance value of 31.42 ohms. Next, we can look at the total impedance of this circuit, which is not as straightforward as doing the resistive component plus the inductive component. What we have to do, use Pythagoras theorem, so we have the true, the resistive component on the x-axis here, and we have the reactive component on the y here. And what we're doing is basically calculating this. And we can do the same thing for impedance. So what I'm going to do here is do the square root of r squared plus xl squared. So this is just Pythagoras theorem. So c squared equals a squared plus b squared. And we get a total impedance of 59.05 ohms. Now using this impedance, we can calculate the current that is going through the circuit. So the current is equal to the voltage divided by the impedance. So we get 4.06 amps. Next, we can calculate the voltage across the resistor, so VR, and the voltage across the inductor, so VL. So the voltage across the resistor is going to be the current times the resistor value, and the voltage across the inductor is going to be current times the inductive reactance. So VR is equal to 203 volts and the inductive voltage is equal to 128 volts. Obviously, if you add these two numbers together, let's call it VT, you get a voltage that is higher than the voltage of the power supply, which obviously doesn't make sense if you look at it in terms of KVL. But what is happening here is you also need to bring in the Pythagoras theorem again. So if you do c squared equals a squared plus b squared again, then you'll get the true voltage that's being applied. So I'm going to copy this equation and use it to get the value for the total voltage. Obviously, I need to look at the inductor voltage and the resistor voltage. So I get 240 volts. So this obviously matches up with what we are supplying. Now let's look at the true power in this circuit. So the true power is the power dissipated across the resistor. So the voltage, so we can calculate this in a number of different ways. We can do I squared R, so we know what I is, we know what R is, or we can do V times I. So we know what the voltage across the resistor is, and we know the current through the circuit. That's going to be simpler to type out, so let's do that. So our true power dissipation in this circuit is equal to 825.9 watts. Now we then can calculate the reactive power in this circuit, which is going to be equal to the current times the voltage across the inductor. So that gives us a VAR, so voltage ampere reactive, of 519. And the apparent power is equal to the input current multiplied by the input voltage. We can also do this a slightly different way by doing the Pythagoras theorem on the true power, which is on this axis, and the reactive power, which is on this axis. So if you want to calculate the apparent power, square root of P squared plus Q squared. So let's do that the other way as well. So we get square root of P squared, which is the true power, plus the reactive power squared. And we should get the same answer on this line as well. So you can see both of these numbers match up. So our input current and the voltage and the power dissipation across the two components. Now let's calculate the power factor for this. So power factor is equal to the true power divided by the apparent power. So in this case, and in this circuit that I've showed here, with the following values, we get a power factor of 0.85. Obviously, this does not have any units. Now let's look at what happens to the circuit when we introduce a capacitor. So what I've done now is added a capacitor to the circuit. Let's now look at what happens to the power factor and the power dissipation when we introduce a capacitor to the circuit, as mentioned in the question. So I'm just looking at the series case for now. So I've added a capacitor here with a value of 100 nanofarads. And obviously we have our inductor of 100 millihenries from previously. If we look at the reactance of the inductor, that is equal to 2 pi f times the frequency times the inductance. So we get 31.42 ohms as before. Now we also need to look at the reactance of the capacitor, which is equal to 1 over 2 pi fc. So that's 1 over 2 pi times 50 hertz times 1 microfarad. And we get a capacitive reactance of 318.31 ohms. The total impedance in this circuit now is different to what we had before. So previously we had an impedance that was equal to this line here. So obviously we had our true resistance, we had our reactive component, and we calculated the impedance with this line. We need to do the same thing now. However, so what we are doing here is taking away the reactance of the capacitor from the reactance of the inductor, and that is squared. So we are still looking at this line, but the Q is now different as we have introduced a capacitor into the equation. We get a total impedance in this circuit of 291.22 ohms. Using the impedance, we can calculate the current through this circuit, which is obviously equal to the voltage, which is 240 volts, divided by the impedance, which is 291.22 ohms. So we get a current through the circuit of 0.82 amps. Now let's look at the voltages across the inductor, resistor, and the capacitor. So firstly, the resistor, the voltage is obviously equal to the current times the resistance value. So we get 50 ohms times by 0.82. And so that's 41 volts across the resistor. The voltage of the inductor is equal to the reactance of the inductor times by the current. So we get 26 volts across the inductor. And then the voltage across the capacitor is equal to the reactance of the capacitor times by the current. So we can calculate the total voltage similar to before by doing the square root of the two squares. However, as before when we did the impedance calculation, we need to take away the capacitive component from the inductive component before we square it. So we get a total voltage of 240 volts, which matches up with our power supply. So then we can go into calculate the true power in this circuit, which is obviously the power dissipation across the resistor. Again, we can do this in multiple ways. I'm going to do P equals VI. So that's basically the voltage of the resistor multiplied by the current. And we get 34 volts across the resistor. The reactive power is equal to the power dissipation of the inductor minus the power dissipation of the capacitor. Obviously that returns a negative value, so I've made that absolute. And the unit for reactive power obviously is VAR. So we can now calculate the apparent power. So as before, we can do this in two ways. The first way is just multiplying the input voltage times the current through the circuit, which we get 198 VA. And the second way is using Pythagoras theorem and this. So we know our true power is 34 watts and the reactive power is 195 watt VAR. So doing true power P squared plus Q squared and all of that square root, we get apparent power of 198 VA. So obviously you can see that the two numbers match up, and this is just a bit of a confirmation that what calculations I've done here are accurate. Next, we can calculate the power factor for this circuit, and that is equal to true power, which is in the resistor, divided by the apparent power. So we get a power factor of 0.17 for this circuit with a 1 microfarad capacitor. So from the art of electronics, we were asked to set the inductor value as 1 over omega squared L. So let's do that and see what happens to the power factor. So what I'm going to do here is set the capacitance value equal to what's been given to us in the art of electronics. So obviously that's equal to 1 over 2 times pi times F, and all of that is squared, and then we need to multiply that by the inductance. So that gives us a capacitance value of 101 microfarads. And you can see the power factor is now equal to 1. So obviously we've massively improved the efficiency of this circuit. Without the capacitor, we had a power factor of 0.85. And now adding the capacitor into the circuit of value 1 over omega squared L, we get a new power factor of 1. So essentially what you are doing with introducing the capacitors in a series or a parallel RL circuit is increasing the power factors to get better efficiency. Hopefully all of this was useful. Let me know if you have any questions in the comment section below. Thank you for watching.